Good afternoon. Thank you for joining us. It's nice to see that we have a nice in-person audience as well as an audience online. We're here today for a talk that's hosted by the Center for Indo-Pacific Affairs. I'm Patrice Flowers. I'm the director of the center and professor in the Matsunaga Institute for Peace and Conflict Resolution. We're very fortunate today to have Dr. Jeffrey Drazen from the School of Ocean Environmental Science and Technology here at UH. Dr. Drazen is internationally recognized for his work on food webs, especially in the deep sea. His recent research has really contributed to our baseline knowledge of environmental impacts of deep sea mining, and that's the topic that he is going to talk with us about today. So thank you very much, and I'll turn it over to you.
Thank you, Patrice. Thanks everybody for coming. Today I'm going to be talking about deep sea mining, and I'm a natural scientist, and I realize this is a very interdisciplinary audience, so there's going to be a few data slides, but I'm trying to keep it to a minimum, and we're really going to overview environmental risks about this topic, but I'm hoping that maybe at the end we can have a bit more of a multidisciplinary conversation about this topic. Okay, because there's a variety of you here that probably are not very acquainted with what the deep sea is. I know some of you are very acquainted with it, but there's a diversity of backgrounds. So I'm going to start there. The deep sea is the biggest ecosystem on the planet. I particularly enjoyed this Google Earth view of Hawaii surrounded by all of this blue. And in the background here, this is the abyssal plain at 4,000 meters depth. And this is a rat tail fish and a bunch of pink sea cucumbers. And it gives you a bit of an idea, and I'm going to show you some more videos. Some fun facts: 65% of the surface of our planet has water deeper than 200 meters. That means that 90% of the habitable volume on our planet is the deep sea. We usually use 200 meters, as anything below that is the definition for the deep ocean. The average depth of the oceans is roughly 4,000 meters. And I think a lot of people don't realize that. That's 12,000 feet or 2.3 miles, depending which units you like to think about. But most of the ocean is very, very deep. And when we visit it, when we go to the beach or go fishing, we are just visiting the skin of the ocean. There is much, much more below that. The environment is very cold. Cold water sinks. It's dark. Light does not penetrate very far through seawater. It's very high pressure. Every 10 meters you descend in the ocean, you add an atmosphere of pressure. So when you get to 4,000 meters, you have 400 times the pressure that you are experiencing here in this room. And it's very low food, simply because it's dark and there's no primary production. So these conditions, while they seem quite alien to us, they are the norm for life on Earth, because these are the conditions you find in 90% of the habitat volume that we have. And I'm speaking about the deep sea as a single place. It's not. It's huge, and it has many different ecosystems and habitats within it. It has abyssal plains, picture one is here. It has underwater mountains, canyons, trenches, high food regions, low food regions, many different types of places. And there is a tremendous diversity of life in the deep sea. The animals and other organisms, mostly microbes, that are in the deep sea make up roughly 50% of the mass of life on our planet. And there are as many species living in the deep sea as you would associate with, these high diversity places like tropical rainforests and coral reefs. And this is just a host of different animals, many of those from the CCZ that you can see there. I would argue that the deep sea is the last frontier on our planet. You'll hear this little quip on the internet: the surface of the moon is better mapped than the bottom of the ocean. Well, it depends on resolutions and things like that. But there is a big project now called Seabed 2030, which is attempting to map all of the seafloor in high resolution. They don't know if they're going to make it. We went to one of the mining zones one time to study a seamount. We were basing our objective off of a satellite gravimetry map. And yes, the seamount did not exist. It was an error in the data. So, we have a long ways to go. It has been estimated that there are 1 million new species waiting to be discovered. Different estimates vary. There's a few that are a couple more million than that. Here are a couple of examples from the waters around Hawaii of new species that we've discovered in our lab. This is Hawaii's first snailfish. It's about 5 or 6 inches long. And this is a king crab from just 1,500 meters depth off of the Waianae coast. And the head that you see there is about the size of my fist. So these are not small, tiny things. They're not little worms in the mud that are still waiting to be discovered. There's a lot of larger organisms in the deep ocean that still need to be described. And we're still trying to understand how our activities as a human society affect this place. I think for the vast majority of people, the deep sea is out of sight. It's dark, and you can't just as an individual go there. You may be able to tune into a nature special on the deep ocean. You might participate in one of these ROV broadcasts from a ship, and in that way go visit the place, but it's harder to do than just going to the beach. And because it's out of sight for many people, it's out of their minds. And that's part of the reason why I'm here today to talk to you, hoping that I reach people who are not familiar with the deep sea yet. Our society is actually quite connected to the deep sea in ways that folks don't realize. So one of those ways is through natural products. On the top left here is a picture of a whale bones on the deep sea floor. Philomene is smiling because she knows this comes from Craig Smith's research. And this is, who's a professor in our oceanography department. These whale bones are full of fat, and an enterprising scientist realized that there were these carpets of bacteria growing on these bones at the very cold deep sea depths, and ingeniously realized, I could figure out what chemicals, what enzymes these bacteria are using to break down these fats, clone them into something I can grow in the lab, and put these enzymes into your laundry detergent so that you can wash your greasy clothes and not have to use the hot cycle. You can just wash your clothes in cold water. That is an example of a natural product from the deep sea. Down here is a coral forest from off of the Big Island of Hawaii, and a number of studies are identifying potential cancer drugs and rheumatoid arthritis, anti-inflammatory drugs from some of these organisms. People also don't realize a number of species that you find in a seafood market may come from the deep sea. These are just a few examples. These are ones I have actually personally tried myself. Rat tails, they have a long tapering tail that looks like a rat tail. Well, you can't market that, so they got renamed grenadiers. And those now show up in seafood markets. They live between 800 and 2,000 meters in various parts of the ocean. There's a number of different species. The moonfish, or opa, very popular in restaurants in Hawaii, really tasty. That animal lives between 100 and 1,000 meters. And this fish here, the thorny head, this lives in the North Pacific, off Japan and off the continental US, between 300 and 1,200 meters. So there are species that you will encounter in seafood markets and in restaurants that actually were harvested in the deep sea. In addition, there's a host of species that we don't think of really as deep sea creatures, but they tap into deep sea food webs. On the right, we have that opa again, but also swordfish. They dive to 1,200 meters to feed on squid. We have big-eyed tuna. Many of you probably have eaten if you've picked up a poke bowl at Foodland or something like that. They dive to 600 meters to feed. So they tap into this food web, very simplified, primary producers, the smallest over here, all the way through plankton, small fishes, to the larger species we like to eat. And you can see that there's a lot of foraging on these deeper portions of the food web, which are diagrammed at the bottom of this slide. Now, the small fishes and squids and shrimps, they actually undergo a really fascinating migration. Many of you have probably heard of this daily migration, but they are living at depth during the day because if they're in the brightly lit surface waters of the open ocean, they get whacked by one of these predators. So to hide in the open ocean where there are no rocks or kelp to hide behind, they dive to death. And these predators have amazing adaptations to hunt them despite the fact that they are at depth. Huge eyes, heater organs on the eyes of swordfish, so their eyes actually act quickly under cold temperatures, crazy stuff. So in addition to that linking our seafood supply to the deep sea, it means that a whole bunch of these organisms are feeding in surface waters. They're taking up carbon, and that's taking it out of that shallow water atmosphere ocean cycle, and they're migrating down to depth, and they're breathing, they're defecating, they're transporting carbon down into the deep ocean, out of the atmosphere, and this is helping us with carbon sequestration and ameliorating climate change. So these organisms are quite important to us. And I just like this slide. I usually put this in for younger audiences, but just keep in mind that when you go and you pick up the poke bowl or the sashimi plate at the restaurant, you're basically one step in the food web removed from crazy things like this. This is a viper fish with giant fangs in its mouth. You're just one step in the food web away from that. Okay, that's the deep sea. Now let's talk about deep sea mining, now that you're a bit more familiar with the where this is going to happen. This is a potential industry. It has not yet started at an industrial level. And there are three main targets for this developing industry that they would like to mine. On the left, we have hydrothermal vents. These are places where superheated water has dissolved minerals from the Earth's crust and from sediments, and that water comes out of the seafloor. It's actually the ocean's spreading centers. And it forms these black smoker chimneys. And what's happening there is all the minerals in the very, very hot water that can be hundreds of degrees is being cooled very rapidly by coming in contact with the ocean again, and it's all precipitating, and it's just falling back down to the seafloor. And over many thousands of years, it forms what are called massive sulfide deposits that have zinc, gold, silver, and copper. And this is happening at depths of roughly 1,000 to 3,000 meters in different places in the ocean. In the middle, we have an underwater mountain, and particularly those that are very old underwater mountains at depths between about 800 and 2,000 meters. Over millions of years, metals that are dissolved in seawater attach themselves to the rocks. They come out of solution and they form these crusts. You can see this thick black layer on the bottom middle picture, and that crust has cobalt, copper, manganese, and nickel in it. In a similar process, but on the abyssal plains at depths mostly of 4,000 to 6,000 meters, you have these metals coming out of solution and attaching themselves to a grain of sand or a shark's tooth, some little object. And again, over many millions of years, they grow into objects that are maybe the size of a golf ball to maybe perhaps the size of your fist, these manganese nodules here, and they have the same sorts of metals that you find on the seamount crusts. The reason that these are of interest today is that it's mostly these two resources on the right, the crusts on seamounts and the nodules on the abyssal plains. Those metals, those are battery metals. That's what we need to build a lithium-ion battery. So all of you have some of those metals in your pocket right now because you've all got a cell phone. Computers, same thing. And now we're talking about electrifying our transportation network, and the batteries in electric cars are many, many, many times bigger than the batteries we use in our portable electronic devices. So we need considerable amounts of these metals, potentially. There are terrestrial sources of these metals, but they're becoming harder to access. There's child labor issues with cobalt mining in Africa that are horrible. There are political issues with getting some of these critical metals from mines in China or in mines controlled by China. And so folks have become increasingly interested in these resources I've just described to you on the deep sea floor. Now, a little bit about sort of the beginning of how we discovered these things just for a moment. The polymetallic nodule here, this was originally trawled up from the seafloor by the Challenger expedition in the 1870s. That's the HMS Challenger pictured there. And at the time, there was a lot of debate about what they were and how they formed and things of that nature. But just to jump forward a large block of time, a number of technological innovations, particularly in the offshore oil and gas industry, made the exploration of these deep sea environments a commercial possibility. And there was a big period of interest in mining these, particularly in the 1980s, late 1970s to 1980s. That kind of went away for a while because there wasn't the big need for the battery metals, but now there is. We're trying to wean ourselves off of fossil fuel, We need batteries for renewable energy. So we also have advanced tremendously in our technology. And so there is a great deal of interest in this right now. Many of the licenses that have been filed with international bodies, the International Seabed Authority, have been filed in the last 10 years by countries and companies wanting to mine the deep ocean. I want to emphasize, testing and exploration are occurring. Companies are testing mining vehicles. They are exploring for resources. Mining at a commercial scale has not yet begun. So this is a developing industry, and I see it as a wonderful opportunity to impart good environmental management. Another important thing to wrap your head around is that the scale of deep sea mining is massive. These are all the licenses that currently exist. Actually, this is just a couple years old, so I think I'm missing a block or two. But all of these brown polygons are license areas and what I'll call reserved areas. I'm not going to go into it right now for mining the deep sea floor. If you superimpose these on the continental United States, you see that they're talking about basically mining an area that would span from California all the way to Pennsylvania. It's massive. So this is roughly 1.5 million square kilometers. There are 30 licenses that have been granted globally. 18 of those are pictured here, some of them that are in multiple blocks. And these resources are in our regional neighborhood here in the Central Pacific. You can see Hawaii on the left-hand side of the map, and these colors denote a rather optimistic view of where these resources might exist on the deep sea floor. Not all of these colored blocks hold enough resource or resource of a high enough ore grade to actually be mined. I want you to focus on a couple of areas. Well, first of all, I'm going to go back. The blue is where there are nodules on the abyssal seafloor. The red are where there are massive sulfide deposits near hydrothermal vents. And the yellow are where there are seamounts that may have those metal crusts attached to them. There's really a couple of areas that have a lot of these potential mining resources. One is called the Prime Crust Zone, or PCZ. It's to the southwest of Hawaii, and it wraps over into the Western Pacific. The seamounts there are the oldest in the world, and so they've had the longest amount of time for those metals to accumulate those crusts. The other area of great interest is the Clarion Clipperton Zone. This lies between us here in Hawaii and Central America, and that's those licenses that I showed you in the previous slide. So we kind of have a front and center seat to this developing industry. The places that are of interest to these companies are in our regional neighborhood. The mining equipment that's going to be used is every bit as big as you may have seen on TV with terrestrial mining. These are just a few images. These are vehicles made for sulfide mining by a company called Nautilus Minerals. And these little yellow dots right there, those are people in reflective coats, safety coats. So they're massive vehicles. On the right is a Japanese vehicle that was used to test mine on Seamount 2 years ago. It's all just test mining, but these vehicles are built. This is starting to become a reality. And I just wanted to show you here. This is a great video by the metals company. They tested their mining vehicle, which you can see right there. It's in partnership with an engineering firm called Allseas. And this is their tracked vehicle for nodule mining in the CCZ. And these are videos from their test in 2022. So the vehicle is controlled remotely from a room in the ship. It's driven like a remotely operated vehicle, like a scientific vehicle would be. It's just much larger. These are pipe sections that connect the vehicle to the surface, and that's what all the ore is rocketed up to the surface ship in. Once that ore comes to the surface, it's all the seawater and mud is spun out of it, and the nodules break up a lot, and you can see all these ore, these nodule fragments being collected there. So that's the basics of nodule mining. For management on the high seas, outside of countries' jurisdiction, this is done by the International Seabed Authority. This is an international agency established by the United Nations Convention on the Law of the Sea. And they have a dual mandate to promote the mining for the common heritage of humankind in the area, basically the high seas on the seabed, and to ensure effective protection of the marine environment. And the ISA has a goal right now to approve exploitation regulations by the end of this calendar year. So this is developing fast. Philomene, who's in the audience, has participated in a number of the activities, and for those directly involved, it may not seem like it's moving fast, but it seems like it's coming up on us quickly. An important part of this regulatory component of deep sea mining is that all the countries that have signed on to the United Nations Convention of the Law of the Sea, this treaty, and are partaking in this negotiation of regulations, there's a clause in there that says that they will ensure equal or better protection in their own territorial waters. So these ISA rules, there's a lot at stake. They matter a lot. They will probably not govern just the high seas, but many countries' exclusive economic zones and how mining may proceed there. Okay, so let's talk about some of the potential environmental risks of deep sea mining. This is that collector vehicle that I showed you in the little video. It is connected to the surface ship by a 2.5-mile pipe. And this collector vehicle, as it drives across the seafloor, is going to pick up about the top 5 centimeters or so of mud with all the nodules. The nodules stay right on the surface of the mud. If they sink too deep, they dissolve over time. So they're right on the surface. And these vehicles are quite large. Ultimately, they're going to be about the size of this room, perhaps bigger. And so you're talking about collecting these nodules in 5-meter swaths or larger. And that obviously will remove these little rock-like things, these nodules, which is habitat. I'll show you some videos of animals that live on these things. And it's going to kill most of the infauna or the organisms that live in the sediment below it because it's going to be compacted as this vehicle drives over the surface. We've also done some studies with small-scale disturbances, and it alters actually the geochemistry of the seafloor after this is all done. This process we expect to impact something on the order of 300 to 600 square kilometers per year for a mining operator. So that's about 10,000 square kilometers over a 15-year license. And in addition to this, and this is an area of active debate, these plumes here are not to scale on this picture. This is so you can see them in this diagram. But these plumes are going to expand beyond the collector, and they may disperse from 10 kilometers roughly to potentially tens of kilometers. And that's just very fine mud on the deep sea floor being stirred up by this mining activity and drifting for long distances before it settles back down to the bottom. That's going to bury animals when it settles. Out in the open ocean, it's very clear ocean water, and the natural sedimentation rates are about a centimeter in 1,000 years. So when you're talking about a lot of the sediment coming back down, the animals are not adapted to that type of a situation. These are not organisms you would find in our harbors that normally see big storms, resuspend a lot of mud and drop it down on them. So they're not adapted for that. And there have been some studies. It's going to bury a lot of animals. One of the estimates suggests that that is going to expand the area of effect from 10,000 square kilometers to about 50,000 square kilometers over a 15-year area of operation. That's the size of Costa Rica. And there's 18 licenses in the CCC right now. So this is a serious concern. Now, I want to show you, we've been to the Clarion Clipperton zone a number of times, and I want to show you a bit of what it looks like. So this is a video that actually Megan Putz made. She's in the audience right there. And this was from an expedition we had a couple of years ago. And that's a cloud from just our little tiny scientific ROV hitting the seafloor. You can see the manganese nodules behind. And these are some of the fascinating organisms that you see on the deep sea floor. These are sponges right here. They're glass sponges, so they make their skeleton out of glass spicules. That's a sea cucumber. Anemones growing on a stalked organism, probably a coral or something like that. Persingid sea star. This is a sea cucumber that actually has a sail. If it doesn't find enough food in its environment, it can put up the sail and drift off into the currents and settle in a new place. This is on a seamount nearby, and that's a coral colony. That's a deep sea lizardfish, it has no eyes. This is the area that we were studying here in these boxes. That is a shrimp. It's about a little longer than your hand. These are actually predators in the deep sea. We're collecting some manganese nodules with what we call the beer stein, but it's an effective way of collecting these animals, and then we look at the organisms that live on the nodules and the microbial communities that live on the surfaces of those. That's another one of the swimming sea cucumbers. That one is actually up and drifting. Deep sea octopus. Couple of cusk-eel fish.
How deep were these images taken?
This is about 5,000 meters. Yeah, some jellies. And that is a sponge right there with a sea star on the bottom of it. Okay, so I hope that gives you just a bit of an insight. There's actually, if you go to that project's website, Deep CCZ or Deep Seas, if you just type that into your web browser, there's a much longer video if you're interested in seeing more of that kind of thing. Our surveys showed, and so have those of many others, that the CCZ fauna is extremely diverse. So here is just some pictures of some of the other animals that weren't in that video, some that were. But we observed over 300 species of what we call megafauna in just a few square kilometers of seafloor that we surveyed. Megafauna in this case is just defined as anything big enough for us to see in our cameras. So it typically starts at about 2 centimeters and goes up to there, up from there. And we discovered that many of the organisms, including this anemone right here, which is in a whole new family of anemones, deep sea corals, a host of sponges, about 50% of the diversity, the taxa that we observed, live on the nodules themselves. It's habitat, of course. There was a nice recent analysis published taking a look at everyone's surveys in this region, and they estimated that 88 to 92% of the species that we have identified, usually just as, you know, this is fish number 1 in this region, are undescribed and are waiting to be described. And the total number of species is estimated at something between 6,200 and 7,600 species in this eastern portion of the Clarion Clipperton zone, this mining area. There's a lot of undescribed diversity. And it's important to realize that the nodules take millennia to form. So they're removed, then their habitat doesn't come back over evolutionary timescales. So the same species will not be there by the time those nodules have reformed. This is just another figure showing a map. All the stars are places that we've deployed baited cameras, like the video depicts in the bottom right, looking at scavenging communities. And we estimated for studies in these different places around the globe, the diversity. And the eastern CCZ is this brown bar right here. There's a really high diversity. And scientists have found similar things with polychaete worms and with small crustaceans and other groups of animals. There's really high diversity in this Clarion Clipperton zone. And the reason is pretty obvious. The nodules are added habitat. It's a different niche. Many areas of the deep sea floor are just mud. But in the CCZ, you've got mud, plus you've got all these nodules. And that added habitat complexity adds diversity to this system. There have been some studies, actually a number of studies now, looking at recovery on these abyssal seafloor ecosystems. And we're discovering we have discovered they're not very resilient. This is a track made by a scientific disturbance experiment, basically dragging a dredge across the seafloor. You can see manganese nodules on the right. You can see the crumbled edge of where this plow kind of went across the seafloor and disturbed the seafloor. Scientists went back 7 years later and they took tubes and pushed them into the mud to count all the small animals living there. They had only returned to about 15% of the abundance that was present before this disturbance was made. And you can see these tracks kind of look quite fresh. I know those of you in the back of the room probably can't see them very well, but they look very crumbly, and they're not sort of smoothed over. How old do you think this track is at the time this picture was taken? There's a couple of you in the room that work in my lab, so don't answer. Anybody have a guess? How old do you think this track was when this photo was taken?
15 years.
Okay, any other guesses? It's 26 years old. So this is not your high schooler driving across the lawn late at night, and then, you know, a couple months later the grass grows over and it's all done. This takes a long time. It's a very low energy environment. Current speeds are not high, the animal abundances are low. And so the activities that would repair these kinds of damaging effects, you know, the recovery rates are just really, really slow. There has been a couple of surveys showing partial recovery of some of these systems, but generally we call it incomplete recovery. There's one really good study called the Discall study that shows incomplete recovery of communities 26 years after the disturbance. One paper by a colleague, Dan Jones, suggests that full recovery may take 100+ years, and that, of course, the nodule fauna can't recover because those nodules grow so slowly. So their animals do come back, but it's definitely not the same community as before. And so we need to consider that the areas, particularly in this Clarion Clipperton zone where there's a lot of license blocks, the areas that are first going to be mined probably won't have recovered by the time the last areas in this zone are mined. So it's not a patchwork of different stages of recovery. We need to think about whole system impacts. So that's a list of, or that's a sort of a description of how we think these deep sea seafloor communities will respond. What are we going to do to protect these? Well, the International Seabed Authority does a couple of things that are really great. First of all, they mandate ecological study. Any country or company with a country sponsor that has taken a license out has to conduct environmental studies of its seafloor ecosystem. They have to create an environmental baseline, and they have to engage in monitoring once they start mining. This is great. The mining regulations are still being drafted, so exactly what they have to do is still a little up in the air, but it's definitely a really good thing. In addition, these green blocks right here that have the letters APEI, that's Area of Particular Environmental Interest, it's a no mining zone. It's a protected area, and they're 400 kilometers on a side. They're very large. And scientists put these together. Craig Smith was the leader of putting these things together. And you can see them here. They're on the outside of this central corridor of license areas. And there was a big workshop in 2018 where scientists put all their data together, and they realized that the locations of many of these actually exclude high nodule habitat. So with a lot of data, the results were put forward to the International Seabed Authority, and they realized that maybe they're not in the best places. They may not represent all of the ecosystems and communities that are present in the mining zone, and they created these red ones right here. So, and for those of you on the marine affairs side of things, you'll be very interested that the United States is not a signatory of the United Nations Convention on the Law of the Sea. And so they have some unofficial areas, license areas, that includes right where the ISA stuck that one right there. That's going to be kind of interesting. Okay, so some work is being done to try to conserve the biodiversity in these areas. But now I want to shift a little bit, move us from the seafloor up into the water column towards the surface. And this is a video, there we go, from the water column. These are amazing jellies that we observed in the Clarion Clipperton zone. And we use remotely operated vehicles, much as we do on the seafloor, and drive transects through the water column to be able to survey all of these animals. These do not get captured in nets very well. That's a pelagic worm called a tomopter, highly bioluminescent. That's a ctenophore. That's a siphonophore, kind of like the Portuguese man of war that may have stung you on the beach. These are deep sea varieties. They can be tens of meters long. They're amazing. Octopus, the yellow mass is eggs. It broods its eggs in its arm. It doesn't feed the entire time it does that. So really incredible animals, but all these jellies and things, they don't survive in nets like these fishes do. And so using multiple techniques has been very valuable in trying to describe what lives in the water column in these areas. Okay, so if we turn our attention to the water column, we're really focusing on this plume here. Again, this is not to scale. This is just a diagram. We think these are actually going to be pancakes. They're not going to be distributed as deep as are shown right there. It's a bit of artistic license. There's going to be noise generated from nodules rattling up a pipe or any other resource for that matter. This is mining vehicle on a mid-ocean ridge or mining for seamount crust. This is just one for the abyssal plains right there. They would all be connected to the surface ship in one way or another to move the ore. That will create noise. They will all discharge a sediment plume. Whether it is in the water column or not is an engineering question, really. But companies are talking about doing that. The unwanted sediment and seawater that's brought up with the nodules that is pumped back into the ocean, it's estimated to be discharged at a rate of about 50,000 cubic meters a day. A 20-foot shipping container is 50 cubic meters. So that's like 1,000 shipping containers of muddy seawater a day. It's a lot. So there are also, we have data and others have data showing that metals do dissolve from these activities. They're mining metals. So they break up the ore, and with lots of new surface area, some of the metal dissolves. We are still figuring out how much. And the models of how big these plumes are going to be, the dewatering plume, this discharge plume, vary, but we think they're going to extend tens of kilometers away from the point of discharge, maybe as much as 40 or 50 kilometers, and they will affect between 3,000 and 15,000 cubic kilometers of seawater a year. So huge, potentially huge volumes of seawater. So the scale of this is big, like it is on the seafloor, is the point. So noise will affect marine mammals and other animals. Mud can clog the gills and respiratory surfaces of organisms. These animals are suspension feeders. A copepod on top, this is called a larvation. It looks like a little tadpole. It spins this mucus house, and it pumps water through it, and it extracts little organic particles from the water column. These kinds of organisms form the base of the food webs in these places. And with all those mud particles in the water column, it's going to be very hard for them to feed. That house is going to get clogged with mud, and so they'll have to make a new one. And filter feeders like that copepod are going to have to sift through a lot of inorganic junk, mud, to get to the organic particles they actually want to eat. There's a study now that shows that there's going to be buoyancy issues for gelatinous animals. Metals may be toxic, and there's going to be reduction in visual communication. And in the midwaters, and I would say definitely more than the seafloor, animals use bioluminescence and really incredible visual senses to communicate, to attract prey. Everybody's seen the movie Finding Nemo, right? You know, the little anglerfish with a lure on its forehead. How does that work if the water's turbid? And we use, you know, they use vision for prey capture and bioluminescence. This is a spookfish with giant yellow eyes. The dome on its head is its skull, and it's transparent. That is a dragonfish in an aquarium. You're looking at the bottom of the aquarium and looking at all of its bioluminescent lights along its belly, fins, and eyes light up. It's pretty stressed out because it just got captured by an ROV. And that's just to give you a sense of what I'm talking about with the bioluminescence and vision. So together, these kinds of effects may lead to mortality, migration, and shifts in community composition overall in the ecosystem. So for a long while, most of the attention has been directed towards understanding environmental risks on the deep sea floor. And that makes sense because that's where the mining vehicles are going to be operating. And that's where most were paying attention. But now that we understand some of the companies may discharge sediments into the water column, there's been a lot of interest focused on studying that portion of the ecosystem as well. It's a very three-dimensional habitat. So myself and a bunch of others from University of Hawaii, Brian Pope and Erica Gertza and Angel White and Sarah Ferrone, and I'm missing some people, I'm sure, Mariko Hata and Glenn Carter. We all got together with some other folks, and we put in a bid to do a midwater ecosystem baseline and try to understand what lives in this portion of this ecosystem. And we did that with the Metals Company. They're the first company that actually called for such a study. And this is their license area on this map. It's called NORI-D for Nauru Ocean Resources. And we've been conducting the very first baseline looking at those systems. So we've used nets and remotely operated vehicles, autonomous sail drones, water samplers, particle samplers, and the goal was to study everything from microbes to fish from the surface to the seafloor. We got a bunch of it done, but I'm not sure we got all of it done, that's for sure. It was a lot. We only had 2 cruises. We had spring and fall of 2021, and we sampled 2 sites. Number 1 in the map is where they were going to test their collector vehicle. That's where the video I showed you comes from. It was in that area. And then site number 2 is a reference zone, about 100 kilometers away. And that is an area that was not supposed to be affected by the mining. And for their collector testing, they discharged sediments at roughly 1,200 meters depth. So I'm going to show you some very preliminary results here, but the big question is, how do you pick a depth to discharge these sediments? So the ISA regulations don't have any specificity except you should try to avoid environmental risk. They leave it kind of open. And there has been so little work in this area that it's hard to answer that question. But we now have some more information that can help us sort of understand this. And I'm going to show you some data today, which was collected by using nets, like you can see there, and you can see all the catch being sorted. And that gives us an idea of the diversity and abundance of organisms living in the water column. And the depth that they had originally proposed, without any information, to discharge their sediments happens to be super high diversity. This is the discharge depth down here, and this is the surface in the top. And these are 3 different diversity metrics. I told you I'd try not to have too much data, but this is one of those data slides. And these dots farther to the right are indicating very high diversity at that discharge depth. So that's probably not a great idea. And hopefully there's opportunity to move where they are going to discharge sediments. We also have discovered that this region in the Eastern Pacific has a high degree of endemism of its fauna. So it has oceanographic characteristics, particularly low oxygen conditions. And so many of the species that you observe in this Eastern Pacific region don't live in Hawaii. They don't live up off of, in the central Pacific. They're regionally endemic. And about 30 to 50% of the fishes at the discharge depth that we collected are, in fact, depending on which time of year we were there, are endemic to this region. So we need to consider that the impacts aren't to the whole Pacific-wide ocean, but to this region specifically. We also surveyed depths greater than 1,500 meters. It's really hard to sample that deep with nets. And these are just a few, I don't know why the video is playing again, but these are just some of the organisms that we captured at those great depths. This is actually a worm that's so large, it's in 2 hands. That's a Nemertean worm. All kinds of fishes and other organisms that we have yet to be able to identify. There are dozens of taxa at these depths that you don't find shallower, and many of them we just can't identify. There's been so little sampling done across the world. So it's a unique community deeper. It's very low abundance, but it's unique and different than other depths. So where do you put the discharge? I don't know. I have an opinion. I think you should bring it down to the seafloor, but that's up to regulators to decide. I think the other important thing to note with these kinds of baseline studies, it's wonderful these companies are doing this work. However, you have to do this kind of work for a long time for it actually to do its intended job. You're creating a baseline because you need to distinguish natural variability in the system from mining-induced change. You need to see what's going to happen. Well, we went there twice. This is a surface productivity map. Green means high productivity. Here's the spring, here's the fall. Highly seasonal, so we know we have seasonal variability, and we saw seasonal changes in communities and abundances of animals like plankton all the way down to 1,500 meters. And there are spatial changes as well. These two little boxes that we sampled are different from each other. The times we went there, we totally screwed up our sampling design. They're 100 kilometers apart. We thought they would be replicates. Nope, they're different. It turns out one is north of the North Equatorial Current and the other one's just south. So they're different. And this is a map right here showing sea surface height, and it's a proxy for circulation in the ocean. Hopefully this will work. There you go. This is an anticyclonic eddy. This is a rotational mass of water, and this is the box we're sampling. And during our spring trip, it just moved right through the system. And it changed everything in surface waters down to a depth of at least 700 meters. So, not everything. It changed a bunch of things. The microbes stayed the same. Clearly, we need more time series. We have a great start of the baseline, but can we actually separate mining-induced change from anthropogenic or natural change? It's going to be very hard right now. Okay, I've got to speed up just a little bit. I want to talk about ecosystem service effects. So a lot of these midwater organisms may be affected by deep sea mining, and those individual effects integrate to the population level and then to the ecosystem services level. And I want to talk about fisheries and seafood contamination. So we've done some work trying to figure out how deep sea mining might interact with fisheries on the high seas. And one of the potential mechanisms is that the noise and the mud that's going to be put into the water column could alter the migration routes of things like tuna and the distributions of those animals. They may just avoid the area. If the discharge of sediments has negative consequences for all the animals in these deep midwaters, then that could kill off the food supply for those tunas and other species, reduction in food supplies. And it's possible that the release of metals, we're still trying to figure out how much metal is going to get released, but the release of metals may contaminate seafood supplies. So this is a figure from waters around Hawaii from my past student Anella Choi's work. And we have a whole bunch of fishes, and this is mercury concentration, and it's on a log scale. And this is the depth that they feed at on this axis here. Swordfish feeding deep with high mercury, mahi-mahi feeding shallow with low mercury. This has nothing to do with mining. This is in the central North Pacific, but bear with me for a moment. We have discovered that the microbes that take the metal, in this case mercury, and make it bioavailable prefer low oxygen deep water. And so where does all the mercury enter the food webs? In the deep sea. If we now have a mining operation that releases more heavy metals into the water column, it isn't unreasonable to assume that some of those microbes may make those metals bioavailable, and they will also enter food webs at those depths. We don't know. It is still an unknown, but it is an interesting possibility. A big question is whether or not fishing and mining occur in the same locations. These are all our mining licenses on the high seas, and all of these acronyms here stand for regional fisheries management organizations that manage tuna fisheries. And we took a look at how much of each management area's catch came from the existing license areas for deep sea mining. And ignore the figure on the right. That's a whole lot of details. The figure here on the left gives the overlap, the proportion of catch on an average annual basis that comes from these mining regions. So here in the Eastern Pacific, depending on which data set you use and what species of tuna you're looking at, between 1 and 12% of the fish catch comes from the existing licenses in the Clarion Clipperton zone. So it is small, the amount of overlap, but it's non-trivial. What was also interesting is we delved into this in terms of individual countries, and we found that there were a number of countries for which 20 to 60% of their catch came from mining areas, and that included a number of small Pacific Island nations. They typically sell their tuna fishing rights to other corporations, but if there is even the perceived threat of contamination and metals in the seafood supply, will they be able to sell those rights anymore? So this could disproportionately affect some countries. So how do we protect these water column ecosystems? So the International Seabed Authority, starting about 4 years ago, actually added in these midwater baseline requirements for the water column, and that's how we got that project funded. So that is great. We're doing water column work now. And this is what I briefly alluded to a moment ago. I think that at least in the case of manganese nodule mining, which I've been speaking mostly about today, if you want to minimize the risk to midwater communities, return the water at least deeper than 2,000 meters, so you're out of that system that affects fisheries, and ideally, take it all the way to the seafloor. You're already making a mess on the bottom with the plume from the collector vehicle. Why make a mess in another location? Keep it all together. So that is not for me to decide. That is up for the environmental regulatory agencies to decide. And I'm going to end with this. I'm the scientist, I share data, I help decisions be made, but ultimately society needs to decide how we're going to proceed with deep sea mining. Hopefully the information on environmental risks will help. We have a host of those, and that is the downside, and the upside is battery metals for electric cars and cell phones, and weaning ourselves off of fossil fuels. So it is not an easy decision to make. I am talking to you again today because a lot of these decisions are being made sometimes behind closed doors at the International Seabed Authority. Some parts of those meetings are open and some parts are not. And so society needs to weigh in. And thus far, that has been fairly minimal. So with that, I want to thank all of my various colleagues and students and postdocs who have helped support all these various research projects, and my funders, the Metals Company, Benioff, Pew, Moore, and NOAA. Thank you very much.
Thank you very much. We'll start with questions from the room. If folks want to have questions, I can field the questions for you.
Matter however you'd like to do it.
Yeah, sure.
Yeah, this was fascinating. As someone with no connection to deep sea mining, I feel like I learned so much about an area that's just beginning. And it's super exciting to think that there's this kind of oversight at the very beginning that's like, hey, let's do this right, as opposed to kind of a lot of the other environmental extractive enterprises we've had thus far. This might be slightly outside of the ecological focus that this talk discussed, but I'm reading a little bit about heritage landscapes and this concept of people having intangible ties to certain natural areas. Uluru, as an example. And obviously when we can go on land, we can see these things, those ties can happen very quickly. But in your talk of mining seamounts that have been forming for millennia, what I interpreted that is possibly some of the oldest kind of mountains and surfaces of our planet. And that kind of filled me with some sadness. And I wanted to ask if in this area of deep sea mining, if there has been an analysis of kind of the cultural reactions to this concept of the seafloor as something of like shared human heritage. I know that's a massive question, and I don't even fully understand the question I'm trying to ask. But yeah, do you have any thoughts on that?
Yeah, that's starting. It hasn't. It's just starting, I guess, is the best way to put it. Uncle Saul, who is a Hawaiian practitioner here in Hawaii, has been to several of ISA meetings, arguing that indigenous peoples, particularly around the Pacific, where a lot of these activities are going to occur, have largely not been consulted. This is what he says. I think some of them have, and some of them haven't. And he brings up the fact that the Kumulipu, which is, the origin story in Hawaiian, starts in the deep sea. And so that's the birthplace of life. And so there are cultural connections. And I think there's more attention being paid in just the last couple of years to what those are and how those get involved in management.
Gotcha.
Yeah,
And then,
which voices are heard and what does it mean, in a practical sense, and the regulations and those sorts of things.
and then just as a quick follow-up, regarding the 9 mining prevented areas, was each delving into a different type of biome in the deep sea? Like, what was the decision?
Yeah, so I scooted over that. Thanks for bringing up that question. So when those were first created was a workshop here in Hawaii, and there was very little data, much less even than I was showing to you. And they realized there was a need for a regional environmental management plan. So this was a workshop that was sponsored by the ISA and I think Pew. And they realized, okay, we know that the eastern end of the Clarion Clipperton zone is more productive waters than the western end. So there's probably different communities in both. We need protected areas in both locations. Okay, we know where some of the underwater mountains are. We should protect some of those, right? And so they had these sort of broad regional perspectives, even though the vast majority of the area had never actually been sampled biologically. So imagine using satellite imagery to create the national park system in the United States. You could get it right, but if you haven't actually been there, there's a possibility you will miss some habitats and some communities of organisms because you're using really broad regional criteria. So that's why the additional ones were added. Yeah.
I was just going to ask, is it possible to go back to the slide before with that question that you had at the bottom there? So under what circumstances could deep sea mining occur? And I just noticed that sort of throughout your talk, it was when deep sea mining is going to happen, when it does, as if it's an inevitability. I think perhaps there's a question here that whether deep sea mining should occur is maybe a more fundamental step that we should be asking ourselves, and that's still a very unsettled debate. I didn't know whether you could maybe talk to that a little bit. In my opinion, so within the Pacific, certainly, a number of states have put forward resolutions for either moratoriums or a precautionary pause. Other states have obviously pushed to have these deep sea mining happen at a faster rate. So I just didn't know whether maybe that was something we could talk about a little bit.
Absolutely. Yeah, it's a really fascinating political landscape. And as a natural scientist and not a policy person, you sort of outlined it very well. Just look at the Pacific Island states. Half of them are entertaining mining in their exclusive economic zones, and the other half have bans on mining in their waters and have signed on to this global pause on deep sea mining. To make things even more complicated, the Metals Company, which is the company pushing forward the fastest, they have funded me. I have co-ownership of data and freedom to publish and all those things. But they are based technically in Canada, and Canada has signed on to the moratorium on deep sea mining. So yeah, there's a lot of difference of opinions. And it's going to be really interesting when the International Seabed Authority meets in March and July of this year. It's also under new leadership, and I don't know exactly where things will go, but they do have a mandate to continue pushing forward exploitation regulations. So I'm sure some of that's going to happen. It's not really the answer you're looking for, I know.
Yeah. I just wondered, when those APIs were developed, the mining licenses areas were already in place when they said
a bunch of them were.
Yeah. So it was sort of,
It was hard.
Yeah,
they did recommend putting some of them closer to where the red boxes, the newer ones, were originally, and they had to push them out because there were existing licenses that overlapped with a bunch of the area.
I think we probably have time for another 1 or 2 questions. I see 2 hands. I don't know if Should we jump in for it? Go ahead.
Thanks so much, and apologies for another governance question.
No, this is
Just
great. This is what I was
as a
hoping
scientist,
for.
I love seeing the images in the video because we're studying governance of, things that matter, right? So I appreciate getting that data and perspective. My question is coming as a geographer, right? We've, in governance, done this bizarre thing where we've separated governance of the seafloor under the ISA from governance of the water column under the new BDNJ treaty. And it strikes me that there's, you would have these APIs and potential new areas under BDNJ that may or may not line up. Should they, and if so, where? And so I wanted to ask, is there any effort, the money's all coming for the science work, mostly through the mining companies, right? But
That's correct.
at the same time, you are getting data about what's happening in the water column, and there might be room to liaise with people working through BDNJ to say we need to protect the water column, and that should maybe also intersect with what's happening on the seafloor. So we have this weird governance world in which we ignore ecological connectivity between, the seafloor and the water column. So I don't know, that's not really a question, but it is around, is there room for the science work to liaise with some of these other governance institutions that are, BDNJ is slowly evolving, but.
Yeah, I think there's definitely room to do that. I think the ISA is trying to work with people who are involved in the BBNJ right now. And yeah, I would be a proponent for protecting whole water columns. They're inextricably linked. The primary production in the surface is the food that fuels the deep sea floor. It unfortunately is not a straight up and down thing because particles drift as they sink through the water column for many months and things like that. But it's at least a start. We so frequently just think in two dimensions because we're terrestrial beings. And in the ocean, it is very much a 3D environment. So yes, we need to put these groups together and we need to protect whole water columns.
I do apologize, but they are quite strict with the use of this room, and this has been wonderful. I hope that we can continue the conversation. I do think that this is part of what we hope to do at the Center for Indo-Pacific Affairs, to think broadly about these transboundary issues, to use the expertise we have here at UH, to cross disciplines and to think together about these issues. I know I learned a lot, and I'm very thankful that I got sort of a beginning to end primer to actually think about, okay, how is the seafloor connected and what does this actually mean in practice? And I do think that this slide actually poses critical questions for all of us. I mean, whether you're, interested in environmental risk, if we're interested in the advantages, you can see how, there's a need to really weigh these against each other and to think how we can act ethically and how we can enact governance in this area. How can we, actually create policies that are going to help us all move forward, hopefully. I mean, it's quite complex, and, it's almost a little bit depressing. Right, that this is, it's like, go ahead, have your environmental changes, but there's also this risk that's included. But everything is always complex, and I'm thankful very much for Dr. Drazen for helping us to understand a little bit more of this complexity. Please join me in giving another round of applause.